Good morning. Today we're doing our second homework assignment on solutions, and this one's on dilutions and colligative properties, among some other things. And here's our first problem, so let's get started. This section is talking about dilution, which is where you take a solution and you just add solvent. So your solute particles, the number of those don't change, but your total solution volume does change. And so you can calculate the new concentration of your solution using this equation. And I'm going to repeat it over here. That is concentration, initial concentration times initial volume will be equal to the final concentration times the final volume. And this actually works with a variety of different concentration units. So whether I'm using molarity or percentages or something else, I can use this equation, which is why it's given as C for concentration and not say M for molarity, because this equation has a broader application than say just molarity. The reason this works is that all of our units of concentration, whether we're looking at percentage or parts per million or molarity, they have the volume of the total solution in the denominator. And so when I multiply by volume, those cancel, and essentially what we're saying by this equation is that the amount of solute particles in my initial solution is the same as the amount of solute particles in my final solution, and so these two things are equal. So here, given this formula, they want to say, how do you solve for C2? And you guys know how to do algebra. If I want to solve for C2, I've got to get rid of V2. Cancel those out, and we find that C2 is equal to C1 V1 over V2. So that's what they want us to pick. So here they're saying, how do I calculate final volume? All right, well, C1 V1 equals C2 V2. They want final volume, divide by C2. And again, as I recommended with your ideal gas law, always solve for what you're looking for before you plug it in. Now they give us the original volume, 0.821 liters. The original concentration, 33.7%. Add the final concentration, 21.4%. And note here that because we set this up with dimensional analysis, so long as your units are comparable, it doesn't really matter what you use. So even though percentages usually use milliliters and grams, the fact that I've got liters here doesn't matter. My percentages cancel out. I'll be left with units of liters. If they wanted milliliters, I can do that additional conversion when I'm done here. 33.7 multiplied by 0.821 divided by 21.4 gives me a final volume, or V2, of 1.29 liters. They did say they want that in milliliters, so 1 liter, 1,000 milliliters. That's going to be 1290. Next, we've got a solution which is diluted to this new volume and this new concentration. They want to know the initial concentration C1, and again, C1 V1 equals C2 V2. To get C1 by itself, I'm going to divide both sides by V1. I get C1 equals C2 V2 over V1. My final concentration was 6 molar. My final volume is 1.20 liters, and my initial volume is 831 milliliters. But note here, if I'm watching dimensional analysis, I will see instantly I've got a problem because the liters won't cancel with the milliliters. So I'm going to convert that to liters. That's going to be 0.831 liters. And now the liters will cancel, and I can see what my initial concentration was in units of molarity. So let's plug this in. 6 moles times, that's 6 molarity times 1.2 liters divided by 0.831 liters gave me an initial concentration of 8.66 molarity. Next question. I have a large amount of an 8 molar stock solution, and what I need is not, of course, that concentration, but I need this concentration. So if I've got C1 V1 equals C2 V2, I have 8 molar solution. And I need 1.8 liters of a 2.50 liter, molar solution. And they want to know, how can I make it without wasting any stock solution? Well, I can solve for V1 here. V1 is going to be C2 V2 over C1. And if I do that, you'll see 2.5 times 1.8 divided by 8, that my initial volume here is going to be 0.563 liters. So how do I make that solution? Well, I'm going to start here. That's my initial volume, and this is my final volume. So I need to go from 0.563 to 1.8. I wouldn't just take this and add 1.8 because then I'd have more total volume than 1.8. So I only need to add the difference, right? If this is my initial volume, that's my final volume. Then what I added was the difference. So I added 1.24 liters to get to 1.8. So I'm going to start with 0.563 liters of the stock solution. I'm going to add water until I reach 1.8. Okay, next, this is again just a dilution problem. They want to know how many milliliters of this solution can be made from this. So they're looking for volume. So Z1 V1 equals C2 V2 by C2. So initial concentration, 12 molar. Initial volume, 30 milliliters. Final concentration, 0.350 molar. My molar units cancel out, and you'll see we'll get our answer in milliliters, which is in fact what they're asking for. So 12 molar times 30 milliliters divided by 0.350 molar gives me 1028 or 1030 milliliters. Next, we've got the EPA sets the limit for arsenic in drinking water at 0.01 parts per million. They want to know, how could I dilute? If I knew that I had a lot of arsenic, then how much water would I have to add before I could get people to drink it legally? So again, we're looking for volume. So C1 V1 equals C2 V2. Divide both sides by C2, so we get the final volume. The initial concentration here is 5.5 parts per million. The initial volume that I've got is 1 liter, and the final concentration is 0.010 parts per million. That's going to be the final volume that I need to dilute that to. I'm going to have to get that up to 550 liters. All right, so this next section is looking at a different type of concentration unit known as equivalence, or specifically to make it concentration, you would say equivalents per liter or milliequivalents per liter. And the reason that we use equivalents is because sometimes you've got mixtures of ions and it's not really clear that I've got, say, sodium chloride or potassium carbonate, because I've got sodium and potassium and carbonate and chloride, and all of these ions are dissociated and you can't say what came from what. But one thing you do know, and that is for every positive charge in solution, there must be a negative charge in solution. So for every mole of positive charges, I must have a mole of negative charges in solution. And so one equivalent is 1 mole of positive or negative charges. That is positive 1 or negative 1. So the way that we get to equivalence is you take the number of moles that you've got, but you have to apply the charge as well. So for instance, since calcium has a charge of +2, then 1 mole of calcium ions would be actually 2 equivalents of positively charged ions, because it's going to be like 2 moles of +1 ions. So that's why we use equivalents, because you're looking at something like a mixture. And for instance here, we say we've got a example solution which has 6 milliequivalents per liter of sodium and 11 milliequivalents per liter of calcium. It's already converted to equivalents, and 3 milliequivalents per liter of lithium. All of these are positively charged ions. And they want to know what's the total anion concentration. Remember, the moles of cations has to equal the moles of the anions. So since these are all cations, we could just add this up. 6 plus 11 plus 3 is going to give me 20 milliequivalents per liter of positively charged ions. Therefore, I must have 20 milliequivalents per liter of negatively charged ions. And you might have a mixture again of chloride and bromide and carbonate and phosphate, but whatever you've got, they've got to add up in terms of equivalents to 20 milliequivalents per liter. Okay, for this next question, we're calculating the gram equivalent for each of the following ions. And so what we see is that one equivalent, we're looking for basically 1 mole of positively charged ions or 1 mole of negatively charged ions, or the equivalent of that. So if I've got +2 charge, then 1 equivalent of calcium is going to be like half of a mole of calcium, because it has a +2 charge. So 1/2 of a mole would give basically 1 mole of positive ions, or the equivalent of that. So if we're going to do the gram equivalent, we're just going to need the mass of the calcium, and we're going to divide it by 2. So the mass of 1 mole of calcium divided by the charge then would be the gram equivalent for the calcium. So let's pull up the periodic table here, and we're going to zoom in on the calcium. Calcium has a mass of 40.08 grams in a mole. So 1 mole would be 2 equivalents. So we're going to do 40.08 divided by 2 to get 1 equivalent. That's going to be 20.04 grams. Now, for potassium, because the charge is +1, then 1 equivalent of potassium is the same as 1 mole of potassium ions. That's 1 equivalent of potassium. So it's going to be the same as the molar mass. It's the mass of 1 mole of potassium. That's 39.1. Next, for the sulfate, because it has a charge of -2, then 1 equivalent of sulfate is going to be 1/2 of a mole of sulfate, because you got a 2- charge. So every 1/2 of a mole gives you 1 mole equivalent of negative charges. So whether it's positive or negative doesn't matter. We divide it by the absolute value, essentially. So now we're going to calculate the mass of sulfate and then divide it by 2. So sulfate has 1 sulfur and 4 oxygens. Go. 1 sulfur, 4 oxygens, gives us a molar mass of 96.07 grams per mole. Divide that by 2 to get 1 mole equivalent of negative charges. That gives me 48.04 grams. And finally, phosphate, PO4. We've got phosphorus, which is 30.97, plus 4 oxygens. So that's the mass of phosphate, and the charge on the phosphate is 3. So 1 whole mole of phosphate ions is essentially 3 equivalents. So if I want to know the mass of 1 equivalent, I need to divide that by 3, and I get 31.7 grams. Next, if I know that normal blood contains 3 milliequivalents per liter, I would need to know how many milligrams that is. First thing I need to know is a conversion between grams and equivalents, and that's what we just did in that last problem. We see that magnesium has a charge of +2 because it's in group 2. So 1 equivalent of magnesium is 12.16 grams. Write that down. Now I can just use dimensional analysis here. If I start with 150 milliliters of blood, and this is per liter, so let me convert that to liters. 1,000 milliliters, 1 liter. I have 3 milli equivalents in 1 liter. So my milliliters cancel, and my liters cancel. And I'm trying to go to milligrams, and here I have equivalents in grams. So the milli means the same thing that it did back in the first chapter that we looked at it. So 1,000 milli equivalents is going to be the same as 1 equivalent. Now we could use this conversion factor. 1 equivalent of magnesium is 12.16 grams of magnesium. And since they want milligrams, there are 1,000 milligrams in 1 gram. My grams cancel. Now I'm left with milligrams of magnesium. So 150 milliliters divided by 1,000 milliliters in a liter gives me 0.15 liters. Multiply that by 3 milliequivalents in a liter, tells me I have 0.45 milliequivalents. Divide that by 1,000, that gives me 0.00045 equivalents, which at 12.16 grams per equivalent gives me 0.0055 grams. Multiply that by 1,000 milligrams in a gram, and I get 5.5 or 5.47 milligrams. All right, this next question, very similar, but now it's a multiple choice, and of course that's the format that we're going to see on the exam. So if the normal concentration of aluminum is 16 milliequivalents per liter, then we want to know how many grams of aluminum are in 2.5 liters of the solution. 2.5 liters at 16 milliequivalents per liter. Uh-oh, you can see I did that wrong. Those were not going to cancel. There we go. Now I need grams, so let's look at the periodic table. Aluminum is 26.98 grams in a mole. Divide that by 3 because it has a charge of +3. That's the number of grams in 1 equivalent. So aluminum 3 plus. So 1 equivalent aluminum 3 plus is 8.99 grams of aluminum. This is milliequivalents, so 1,000 milli anything in 1 of that thing. 1 equivalent aluminum is 8.99 grams aluminum. Equivalents cancel. We should be left with grams. So 2.5 liters multiplied by 16 milliequivalents per liter divided by 1,000 milliequivalents per equivalent multiplied by 8.99 grams in 1 equivalent gives me 0.36 grams. Now, if you calculated 360, then you probably just forgot that conversion factor there. And if you calculated 1.1, you probably forgot to divide the molar mass of the aluminum by 3. It's looking like. Next, calculate osmolarity. Osmolarity is a unit of concentration related to molarity, where we take the molarity and we multiply it by the total number of individual things that are actually going to be dissolved or dissociated in solution at that molar concentration. So for osmolarity of covalent compounds which do not dissociate, let's take CH3OH for instance, and if I put that in water, then if I have 1 molar CH3OH, so if I have 1 molar CH3OH, because this is covalent, it does not dissociate, then it only dissolves that one thing. That gives me 1 osmol solution of CH3OH, because covalent compounds don't dissociate. But if I do dissociate, for instance NaCl, a 1 molar NaCl solution that dissociates into 2 ions, so that would be a 2 osmol solution. Essentially, I take the molarity and I multiply it by the number of things that dissociate. So if I had a 1 molar MgCl2 solution, that's going to dissociate into 3 ions. That's 1 magnesium and 2 chloride ions. So that's going to be a 3 osmol MgCl2 solution. So here, I just need to calculate molarity and then recognize that sodium chloride has 2 ions, so multiply it by 2. And molarity, as you know, is moles per liter. So in order to get molarity, I just need to convert grams to moles, divide it by liters, and I'll have molarity. So 370 grams in 2.7 liters. And according to my periodic table, chlorine is 35.45, sodium is 22.99. 22.99 plus 35.45 gives me 58.44 grams in 1 mole. We're talking about NaCl. So grams of NaCl cancel, and we're left with moles per liter of NaCl. So 37 divided by 2.7 divided by 58.44 gives me 0.234 moles per liter. That's the molarity, and remember they want osmolarity, so I have to multiply that by 2 because there are 2 ions that will dissociate. So that gives me 0.468. Oh, excuse me. This is 370 grams, not 37. That's what I get for having poor writing on this thing. There we go. Multiply that by 2, 4.68 or 4.69 osmol. Excellent. Isotonic solution is 0.3 osmol. So if I want to make a 0.3 osmol solution with KCl, since KCl has 2 ions, then I need only make a 0.15 molarity solution, right? Because whatever molarity I have, I multiply it by 2 to get the osmol because it's got 2 ions there. So what I really want is a 0.15 moles potassium chloride per 1 liter of that KCl solution. And they're telling me I need 655 milliliters or 0.655 liters of that solution. So that's the number of moles of KCl I'm going to need. And now they want grams, so I'm going to pull up my trusty periodic table. And potassium is 39.1. And chloride is 35.45, so a mass of 74.55 grams per mole. So here we've got 0.15 moles per liter times 0.655 liters multiplied by 74.55 grams per mole gives me 7.32 grams KCl. Next, we're comparing osmolarity. And we have different molarities, but then we also have different kinds of things. This is an ionic compound, which will dissociate into 5 ions. That's 3 sulfate ions and 2 iron ions. This is an ionic compound that will separate into 3 ions. This is a covalent compound, which will not separate into ions. And this is an ionic compound that separates into 2 ions. So if we parse this out, 0.75 molar, multiply that by 5 ions, what I really have is a 3.75 osmol solution for the first one. For the next one, I have 3 ions, so 1.1 times 3, that's going to be a 3.3 osmol solution. For that third one here, because it's covalent, it does not dissociate, so I multiply it by 1 because there's only one thing there. That'll still be 2.8. And the 1.5 molar, multiply that by 2 things because NaCl only has 2 ions, and that is a 3 osmol solution. So of those, that one is the highest osmolarity. All right. Now, these next few questions have to do with what we call colligative properties. That is, the properties of solutions that change as we change the concentration of the solution. So what they're telling us here is that for every mole of non-volatile solute, the boiling point of 1 kilogram is raised by 0.51 degrees Celsius. So the non-volatile solute is telling us the number of things that are dissolved. So we were looking at osmolarity. But in this case, you're looking at sugar, which is the same as the molarity. So that's not a big deal. We see that 1 kilogram of water will go up by 0.51 degrees Celsius for every 1 mole of solute. All right, so one thing to look at here, kilogram of water. That's an interesting way to look at it. But water is 1 gram per milliliter. So 1 kilogram, which is 1,000 grams, 1 kilogram, which is 1,000 grams, is like, that's 1,000 times, 1,000 times. That's like 1 liter. Okay. So this is like saying that 1 mole per liter, or every 1 molar solution, is going to raise that temperature by 0.51 degrees Celsius. All right, so what if we had 530 grams of cane sugar in every 2.4 kilograms of water? 530 grams of sugar in every 2.4 kilograms of water. And they even gave us the molar mass, so that was nice. 342.3 grams per mole for sugar. So grams of sugars cancel. We have moles per kilogram, which is the same as moles per liter, really. .645. That's It's moles of sugar in every 1 kilogram. Or in other words, a 0.645 molar solution. So that's how much we've got in 1 kilogram. Multiply that value by 0.51 degrees Celsius. And we see that the temperature at which the water boils will increase by 0.329 degrees Celsius. Now they want to know not how far does it go up, but what the new boiling point is. Since water was originally 100 degrees Celsius, now it's 100.33 degrees Celsius, or 100.3. Your numbers might be different than my numbers, so be sure to follow the ones that you've got and not the ones that I've got. All right, which of these will have a higher boiling point? The more concentrated the solution is, then the higher the boiling point is raised. So here we go, 3 moles in half a liter, or 1.5 moles in half a liter. Both of these dissociated to 2 ions. So we want to do this mathematically. We just calculate the molarity, multiply by the number of ions. And I could do that in my head, but let's do it on paper. 3 moles KOH in 0.5 liters. Multiply it by 2. Gives me 12 osmol solution. And here I've got 1.5 moles lithium hydroxide for every 0.5 liters. Multiply that by 2 ions, and I get, that's a 6 osmol solution. So since the KOH is the more concentrated solution, it will have the higher boiling point. So same story here. Here I have the same number of moles and the same amount of water, but this has 2 ions and this has 4. So this one is going to be more concentrated. It has a higher osmolarity because both of these are going to say 0.4 moles divided by 0.5 liters. That's going to multiply by 2 ions. That's going to multiply by 4 ions. And finally, looking at osmose and osmolarity, we see that water travels towards the side that is more concentrated in order to make it less concentrated. And let's see, we've got these 2 membranes. The water will travel towards the more concentrated one, which means the less concentrated one will experience a decrease in volume. Here, if I've got these 2 solutions, water travels towards the section that has a higher concentration. So the section that has the higher concentration will experience an increase in volume. And what do each of these mean? Isotonic means that I have just the same concentration inside of the cell as outside of the cell. Hypertonic means I have a higher concentration outside of the cell, so water leaves that cell and that cell is going to shrivel. And hypotonic means I have a higher concentration inside of the cell, so water enters the cell until it can exceed that capacity of the cell and it will burst. That's hypotonic. Okay. This process is called crenation. This is hemolysis. So hemolysis as in lysis or breaking that red blood cell. So in order to prevent that, you have to have an isotonic solution. So you're looking at 0.9% mass per volume of sodium chloride or 5% of glucose mass per volume. So what we're looking at for this particular problem is we want to compare the concentration of the solution to the concentration of the isotonic solution, because as we just noted, that if my concentration of the solution itself is higher than that of the cell, that's hypertonic, and I'm going to get crenation. So any of these concentrations that are higher than 0.9% for sodium chloride or 5% for glucose, that's going to do hypertonic crenation. So let's see, solution A, that is higher, so that's going to do crenation. Solution B, that's lower, so that's going to go the other direction. That will be hemolysis. Solution C, that's essentially 0%, so that's much lower, also hemolysis. Solution D, that is higher than our 5% for our isotonic solution, so that would be crenation. And solution E, if it contains both glucose and sodium chloride, even if each of those independently is isotonic, when you put them together, it's basically twice as concentrated as it needs to be. So that will also contribute to crenation. All right, that is it for this homework assignment. I hope that this helps. Have a great day.